All right. Thank you, everyone, for attending today's webinar, Real-World Nonlinear Mechanical Applications, brought to you by Design World Magazine. We would like to thank our presenters for being here today and their respective companies, MSC Software and ComSol. I'm Laura Carabine, Senior Editor, and I'll be your moderator today. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, use the hashtag DWWebinar. We will have a Q&A session after the presentations. You can go ahead and submit your questions, and we'll ask them after the presenters are finished. Our first presenter is Dr. Srinivas Reddy, Senior Product Marketing Manager at MSC Software, where he works with a range of simulation products. He has a PhD in engineering mechanics, and his experience includes leading several consulting projects in nonlinear analysis, material modeling, and software customization. Our second presenter is Dr. David Kahn, Vice President of Sales at ComSol. He received his doctoral degree in applied mathematics from UCLA and established ComSol's Los Angeles office in 2001. Again, presenters will be able to answer questions after both presentations. Now, without further ado, I'm handing the mic over to Srinivas.
Thank you very much, Laura. So in this presentation, I am going to talk about the challenges of nonlinear analysis and also some technologies available to you. And we'll also see several examples throughout the presentation. So designers and manufacturers face all kinds of product development challenges and have to find answers to questions like the ones shown on this slide. Whether can I build it, or is it durable, and is it safe, can I test it, and also will it fail, and if it fails, why it has failed, so that we can improve it next time. Conducting the physical prototyping and also the testing ensures that the actual products can be built and tested and also would function as intended. But this is typically an iterative process and also a very expensive process as well, because it involves physical experiments, and sometimes they are destructive in nature. And so just after one test, it renders the prototype useless. And the more complex the product is, the more prohibitive the cost can be. So you can reduce these high costs and also the risks associated with the physical testing using the CAE methods like the nonlinear finite element analysis that can be used to conduct the virtual testing. You can also make better design decisions earlier on in your product life cycle using FEA and nonlinear FEA specifically. So on this next slide, you'll see several examples where simulation has helped our customers in solving their design problems. For example, the very first one, it shows it's an example of a ball hitting a racket. You can also look at it in a different way. You have, for example, a window manufacturer might also be interested in looking at how a stone or another object could hit a screen and how the screen would perform. The next one is a brake model, and here the challenges are definitely multifold. First, we need to know how long it takes to stop the wheel, and find out how much these materials, the different parts, heat up. And there are also issues of brake squeal and also material loss due to ablation and so on. Next, we have a part that undergoes the shearing and finally tearing due to failure. And at the bottom, you see actually a washing machine seal analysis. Here, the manufacturer wanted to know whether and how the seal would buckle and how they could prevent it. And you also see a couple of other examples with bolt loading and shearing, and also a pipe impact example. So on these examples, you see that how a product would perform under design conditions. So on this slide, another big challenge, of course, is the simulation of the actual manufacturing process itself. So coming up with appropriate process parameters for any of these various forming processes that could include roll forming, superplastic forming, hydroforming, or blow forming, and any of the other processes can be very challenging. And also processes like the cutting, either riveting or extrusion. In those things, you also need to worry about the residual stresses and how they could distort the component and how it could affect the part's performance. So we need to understand all these situations so that we can design better products. So we need to see about what is common to all these examples on these slides. So they're all definitely nonlinear in nature. And what exactly do we mean by nonlinear? So in simple engineering sense, it means that the response does not correspond with inputs in a linear fashion. So for example, on this graph here, if the force is directly proportional to displacement, well, you only need to figure out response for one set of input loads. Magnitude doesn't matter, but at just one point. And then once you have that solution for higher loads and any other additional loads, you can apply the superposition principle and get the answer you need. But as you know, even in everyday applications, we see that that definitely is not the case. If you look at a paper clip or a rubber band or even a fishing rod, these are just a few examples that remind us every day that the nature is truly nonlinear, and we do need to analyze our designs as such. So now, let us look at some of the sources of nonlinearities. So whenever the stress is not proportional to strain, the behavior is nonlinear, and we call it the material nonlinearity. So when metals experience loads that go beyond yield conditions, the behavior would be nonlinear. And similarly, either plastics or elastomers or shape memory alloys, these are just a few examples. And as engineers, we do need to account for all these nonlinearities when you design the products. And secondly, the large deformation is another source of nonlinearity. Examples like buckling or any kind of folding that you might see in the structures, and also any kind of large rotations. Those are some of the examples. Next is any changing boundary conditions. So if the applied loads on a body continue to change based on some criteria that you may not be able to predict, you have a nonlinear problem. So for contact, of course, is the most common one. So contact between various components, with that, you may not know how each part would interact with the other parts, and what the contact area is, and how long it's going to last, and how hard it's going to push, and so on. And also, in addition, like one clear example, if in case of rubbers, self-contact, or in other terms, the contact with itself because of some foldings that are taking place, that is a very common occurrence. So that is another thing that we need to account for. And finally, any kind of multiphysics interaction that can change the material response, and that in turn could lead to the nonlinear behavior. So in the previous slide, we saw that the major sources of nonlinearities are what they are. And let us now look at the challenges involved with the nonlinear analysis in tackling all those situations. So first of all, yeah, you need a software solution that can provide you with a appropriate constitutive material models so that we represent the materials more accurately. And also, any solution you use should provide support for large deformations and large rotations, and also the contact modeling as well. And in addition, performance and robustness are the key factors because, again, remember, these nonlinear problems can be resource intensive and they can take longer to run. And we'll look at each of these topics in greater detail in the next few slides. So depending on the application, designs can be made up of different materials. Also, metals are traditionally used. Now, more and more we see elastics and elastomers and plastics more commonly being used in design. And we shouldn't forget that they do exhibit nonlinear behavior even at small strains. So it's very important to understand their behavior and also to model accordingly. You can't definitely use the same models that were used for metals. And the same is true for shape memory alloys or any of the other materials as well. And also we are seeing the use of composite materials rise very significantly. And but at the same time, we should also acknowledge that designing them and testing these composite structures can be a very tedious process. And at MSc, we have been working on improving the composite material modeling, covering all the aspects ranging from curing all the way to the service load performance and all failure as well. So in addition to modeling the actual constitutive behavior of a material, it's also very important to understand if the structure is going to fail, and if so, under what conditions. Different materials can exhibit, they do exhibit different failure mechanisms. And for example, ductile damage is a very common mode in some metals, whereas elastomers undergo continuous damage that can weaken the materials. And also the composite materials, they experience several modes, which could include delamination, fiber pullout, and also crack propagation, which could go across the multiple layers. And again, concrete, for example, it exhibits a very brittle behavior, and it can experience cracking under tension, and also crushing under compression. So once again, these are all difficult problems to tackle, and we have been focusing on addressing these issues as well. And we do provide multiple material models that do support the failure of these various materials. And large deformations and strains, they're a very common occurrence when you're doing a nonlinear analysis. And let's see how these are handled. So it is very important to realize that the traditional definition of the strain is not valid at these higher deformations. So you do need appropriate strain and stress measures, and also element formulations that are designed to handle these scenarios. And of course, there is another challenge with large strains and distortions. First, you may not know where the actual high stress regions are in a component. So you can guess where the high stress would be and have the mesh accordingly. And of course, then if you get it wrong, you would have to redo the analysis by readjusting the mesh. And the other approach is you could have very fine mesh all along, and but the problem is it can be very resource intensive and can take very long to run. On the other hand, if we have an automatic approach that uses local remeshing methods, we can make this process much simpler. So here in this top movie, you see that as the stresses are getting higher, the elements are getting smaller. So it is the software is refining the mesh locally, and so you can get better stress and strain gradients wherever there are higher gradients in the structure without user intervention. And there's another issue that this can occur when either locally or globally where something can get highly distorted. So in this scenario, what happens is the elements can get highly distorted too, and some of the elements can turn inside out, and that can lead to non-positive stiffness matrix, and which means like that would just lead to numerical problems for FEA codes. There are some manual approaches whereby you run this, and once you know where the problem is, you can go back and manually update the mesh and rerun the analysis. Once again, for problems with very large distortions, this can be very, very time consuming, and they may not come up with a solution in time. So a better approach is to once again use an automatic method. And here, the solver, the FEA solver, recognizes the need for a new mesh. It looks at the locations where the mesh is highly distorted. And then a new mesh is automatically created. And of course, the prior state of the structure, including all the stresses and strains and also deformations and temperatures, they're all mapped onto the new mesh so that you don't lose this vital information. So here in the animation at the bottom, that is what you see. You can see that mesh is getting updated as the structure is getting deformed. You can, I'm showing a simpler example there, but you can also do the same thing for 3D models as well. So next, let us look at contact. Contact, or in other words, the interaction between the various components in an assembly or even different assemblies. It's a very common situation that you generally need to model when you're designing any product. So this not only helps you provide better input loads, but also obtain better results. But the problem is often you don't know where and how these different components come into contact and how long they stay in contact. And at MSc, we have invested in enhancing contact analysis on two fronts. So one is making it more accurate and efficient. And secondly, making the setup process much easier and more intuitive. So with this approach, you don't have to know which bodies come into contact, where and when, and so on. So all these things are automatically determined as the solution progresses. All you, as a user, you need to define is your components that could come into contact as contact bodies. And of course, friction and any multiphysics effects, including thermal and coupled effects, can also be modeled, and they are also studied more easily with this approach. It also works very well with the remeshing processes that I mentioned on the previous slide. So whenever the new meshes are created, the contact body information is also retained very well. Finally, with the simulation becoming part of, I would say, everyday design task, engineers are running more analysis and more design iterations. So this means computational performance becomes very important to meet delivery times. MSc is providing solutions on different fronts in delivering performance. First of all, the solvers are being improved continuously and with each release so that we achieve better efficiency. And also the multi-core desktops, they're becoming very common nowadays, and parallel solvers are provided so that you can take advantage of these systems. And also, they can also take advantage of the GPUs that are generally underutilized on most computer systems. And additionally, a method called domain decomposition method can also be utilized. So this can deliver much better scaling. So what happens with this approach is every single task of the FEA solution is parallelized. By that I mean like with reading input files, stiffness matrix assembly, matrix solution, and output generation. All these tasks are run in parallel. So which means you achieve more efficiency in your solution process. And you can connect all your desktops available to achieve this process. So you can, because of these efficiencies, you can achieve both linear and even sometimes superlinear scaling, especially for larger models. So at this point, I'm going to quickly go through a couple of case studies that involved a couple of our customers. So the first one is involves a ship boot development by an automotive supplier. The company here needed to accelerate the boot development to satisfy the requirements of OEMs by developing more design iterations in much less time. The objectives are kind of multifold. First is to accurately simulate the deformations, and also to predict and identify any kind of high strain areas for fatigue, potential for fatigue or any tears. And also the boot needed to pass hot and cold durability testing as well. So here, of course, there are several challenges. The material is nonlinear; it is elastomer, and of course, there are several parts that are coming into contact. So MSC's MARC solution was used to solve this particular problem with contact analysis, and the various stages going from all the way from the molded state of the boot to the various loading cycles are simulated in this analysis, and at the end they did meet the OEM requirements at much less cost. So here is another case study that involves an aluminum product manufacturer. And tensile and compressive instability in sheet metal forming processes causes very serious defects in the design of products. So correcting this problem prior to doing this task, it was done in trial and error method, and it was extremely costly, very inefficient, and also very time consuming. So in this case, customers developed their own methodology using the nonlinear analysis as the driver. And so in this case, once again, the MARC solution was used to, because of its strength in predicting the performance of the drawing process itself, the simulating the actual process. So they embedded that into their entire optimization process over here. Once again, the challenges are there's a lot of contact and also very high plastic strains in this particular model. So with that, let me quickly summarize what we have covered in this presentation. So we looked at the various challenges in performing nonlinear analysis. That includes material modeling and also challenges due to high distortions and accuracy issues, and also both the ease and accuracy of contact modeling and any other coupling effects. And we have also seen some examples where the nonlinear simulation can help improve your accuracy, and also look at some of the technologies that are available for you and that you can benefit from and improve your efficiency. Yeah, thank you very much for listening, and I'll be happy to answer any questions you have during the Q&A session.
Thank you very much, and you can take it away, David.
Fantastic. Thank you very much, Laura. Appreciate it. And thanks, Srinivas, for that presentation. I enjoyed it very much. Let's see. So what we'll do today in my part of the presentation is I'll cover nonlinear mechanics in COMSOL. Now, for those of you who are familiar with the simulation industry, you'll know that kind of MSC is one of the most storied and reputable FEA companies on the market, and we're kind of the new guy on the block. We've in relative terms, been released much shorter amount of time, and we do respect everything that MSC has brought to the market for sure. Since the days back at Caltech, McNeil and Schwindler, making this real industry we owe a lot to. And so I totally agree with Srinivas when it comes to the value of simulation. For sure, I think it goes without saying that simulation has become a part of what we do as engineers these days. And I believe that what I'll be able to cover today will show you the benefit of using simulation, in particular with respect to multiphysics. Okay. Having a little trouble advancing the slide here. Not sure why that would be. There we go. Okay. All right. So we're going to cover now is the multiphysics approach. So when it comes to COMSOL, it goes without saying that we touch on multiphysics. And so what multiphysics really gives the perspective that it gives is really in relation to the historical perspective of simulation. Of course, simulation back in the day was kind of segregated into various subfields due to the fact that there was a limited amount of computing power, and even the theory and the methods were yet undeveloped. We're talking, 1950s, 1960s at this point. And so what developed over that time was some very good and very efficient methods and computing algorithms to do various subfields of physics. And you have a list here: electromagnetic fields, heat transfer, and of course what we're focusing on today, which is structural mechanics. But I point this out just because it deserves saying that what COMSOL, kind of our approach has been since the beginning, is to consider all of these things as just a part of physics and allow the aggregation of these different types of physics into any model at any one time. So, if you want to do structural mechanics coupled with heat transfer, electromagnetic fields, etc., you are certainly able to do so with our formulation of what we do with the actual physical problem. So I just like to point that out because that's our, something unique that we bring to the market and have done so since the beginning of the company. Okay, so with respect to structural mechanics in particular, I'd like to just point out the structural mechanics branch that we have within COMSOL. Of course, structural mechanics is a very large field, and there's a lot that we develop just within this branch. And so we'll cover some of this today. But you also can see here the other aspects of structural mechanics that we kind of deliver directly with COMSOL. For instance, thermal stress, poroelasticity, for geomechanics, and we have the more traditional methods like the shell and the beam and the truss, but also electromechanics, joule heating and thermal expansion, and piezoelectric devices. All this comes kind of due to the fact that the way multiphysics is built into COMSOL. But let's take a look more specifically at structural mechanics and kind of where this kind of mechanical nonlinearity, which is what we're talking about today, where these things come from. Of course, Srinivas has shown you kind of a similar slide, and I think very eloquently mentioned how these sources of mechanical nonlinearity come in. And I would also just kind of like to review this as well. First place that mechanical nonlinear comes in is in geometry. If you bend something too much, then there'll be a kind of a nonlinear relationship between the material between the displacements and the stresses and strains. So that kind of nonlinearity comes in directly through the geometry. The material properties also are nonlinear. Rubber bands are the kind of the obvious thing to think about when you're talking about nonlinearity. There's a nonlinear relationship between the stresses and the strains. That's what this sigma and epsilon refer to. And then contact, this kind of boundary nonlinearity that occurs when something is pressing against something else. You get this kind of contact, which is another source of nonlinearity. And now what I'll do is just kind of cover these in step-by-step form. Geometric nonlinearity, just like to point out here, and the way that it's kind of formulated within COMSOL. I think there's kind of two different ways of kind of considering this type of nonlinearity. The first way is to look at the equations. Of course, you may or may not want to look at them, but it's probably worth just taking a quick peek and noticing the difference between the linear relationship and the nonlinear relationship. When you're talking about small displacements on the order of 1%, maybe less than that, you can have this small displacement theory, which is over on the left-hand side. The main thing to notice is that these epsilons are in a linear relationship with the derivatives of the displacements. Those u, v, and w, or the u and v, those are the displacements, in this case for 2D. So you get an idea of how that small displacement theory works. But if you look over on the other side, the Green-Lagrange strains, you see those have nonlinear relationships between the strains and the displacement. So you see those the derivative of the displacements there, showing you that there's kind of this nonlinear relationship. And that's the way, kind of in a theoretical way, that you can capture geometric nonlinearity. You just add in the nonlinear parts, but it's kind of similar to a second-order Taylor series expansion, something along those lines. Anyway, you get the idea that there's the reason why you can incorporate geometric nonlinearity is because of a more complex equation system that you can resolve. Of course, it doesn't come for free. You have to solve it, and it takes, oftentimes takes more sophisticated methods to do so, but that's the theory behind it. Now, that's one way of looking at geometric nonlinearity in COMSOL. The other way of looking at it is this little thing in the middle, this little checkbox. And so in COMSOL, when you want to just include geometric nonlinearity, there's not a lot. You don't have to worry about the equation. You don't have to worry about programming or anything special. You just do a little check mark, and then COMSOL will include that for you. But it's often good to know exactly what you're solving when you're doing a problem. And so that's kind of what we like to show in terms of our geometric nonlinearity. So the user interface will capture the theory behind it without too much pain. The second part I'd like to talk about is nonlinear constitutive laws. This is the material nonlinearity that we talked about before. And we basically and roughly categorize it in two different categories: hyperelastic constitutive laws and elasto-plastic constitutive laws. Of course, in COMSOL, you can also add in your own user-defined constitutive laws, but these are two very common ones. Hyperelastic, obviously rubber, but also biological tissues also often fall into this category. And elasto-plastic constitutive laws, these are things that can handle metals and plastics. And one very interesting aspect is soils and concrete in compression. We have found that a lot of users in the oil and gas industry have a lot of interest in how to model the mechanical behavior of soils and man-made structures like in concrete. And so the elasto-plastic constitutive laws come into play there. Interesting thing about elasto-plastic constitutive laws, you notice that there is kind of a hysteresis effect where after a certain plastic regime you start having this kind of backwards movement in the relationship between the stresses and the strains. So what can I say about hyperelastic materials? Well, I just briefly mentioned that there's this function called the strain energy density. And so really when it comes down to hyperelastic materials, it's this model that you want to capture. And so COMSOL offers Neo-Hookean, Mooney-Rivlin, and the Murnaghan possibilities in terms of specifying that. You can also do a user-defined hyperelastic nonlinearity here. And here you see a couple of the models. These are, again, kind of seal-type models where it's made of rubber and you want to see under deformation how it would react. So you kind of get this idea. And again, in COMSOL, it's a matter of in the user interface, which is what you see on the left-hand side here, how to set that up. You can set up your material model using a pull-down menu. the material models, the material inputs like the bulk modulus, Lemay constant, etc. Those kind of come with whatever material you're dealing with. We also have this little check mark for incompressible, nearly incompressible material, which basically adds a little bit more complication to the model. Basically what happens when you check that box, you get another degree of freedom to calculate the pressure to make the calculations a little bit more stable. So that's hyperelastic material models. The other one is the elasto-plastic materials, and these are defined by these two regions of mechanical behaviors, the elastic region and the plastic region. So the elastic region, you see this sigma sub y, that's kind of where things are behaving quote-unquote normally. There's a kind of a linear relationship between the stresses and the strains. But then things start bending and kind of turning over, and that's when you're into this plastic regime where there's these irreversible strains. You can see here this little snap hook fastener. It actually is made of an elasto-plastic material. So if you kind of were to bend this back and forth over with a lot of stress, you would actually go into this plastic deformation, irreversible deformation. In COMSOL, you can go ahead and specify the hardening model. It could be isotropic, kinematic, etc. And we also have the different types of equations that you could put in there. We'll show those equations to you. You don't have to actually input them in COMSOL, but we always like to make sure you know kind of what you're getting when you're doing this type of model. So that's elasto-plastic materials. The other source of nonlinearity that I'll touch on today is contact. And so here you kind of see a little bit of the details of how we implement that in COMSOL. You see the snap hook fastener again. Obviously this little block and this little hook are in contact there, and they'll run it in there, and you kind of see the stresses and strains that are associated. Of course, the hard part here, and kind of what some of us touched on a little bit, is in how to specify the different locations where there is that contact. And so COMSOL gives you a very flexible way of selecting the areas, or I'm sorry, the boundaries that will touch. And so that kind of thing, you need to take a lot of care in terms of the meshing that goes into that, etc. So there's there are some challenges related to contact, and you like to get it right. The other thing I like to mention here is about multiphysics. The neat thing about COMSOL is that, you know, when we have this kind of behavior where there's this kind of contact between two things, things can change in a hurry. So for instance, you can imagine if this snap hook fastener was made of some kind of a metal, and there was a current flowing from one side to the other. So in other words, this could be like a switch. And so when these two things would touch, there would be a current flowing from one to the other. And so you can actually add in a very significant amount of multiphysics behavior to a contact model due to the fact that different physics would be enabled by the contact. So those kind of things are kind of the benefit that COMSOL brings to the simulation industry. You can do a lot together with even complicated nonlinear models like this. I'd like to kind of wrap up my part of the talk here by giving you an experience of one of our users. This company, Metelli SPA, they're in Italy, and they are an automotive component manufacturer. They make brake components in addition to water pumps, different transmission components, etc. And they made a really advanced model of that you'll see here. Actually, their experience started by doing a magnetic clutch model. That's that 2D model that you see right in front. And so they actually came to COMSOL with more of an electromagnetics expectation of the software. And so they were able to do that. And this is not unusual among the COMSOL community. You come in for one thing, but then they realize, oh, okay, let's go ahead and start delving into COMSOL a little bit more, maybe we can use it for some other things. And so they were able to develop this model for the CV joint. You see a photo of that CV joint in the lower right corner there. And it's interesting because you have these spheres that are touching the casing on the outside. There's a lot of contact going on. There's also a hyperelastic material model. That's that boot seal that you see kind of stretching out there. And obviously there's going to be nonlinear geometry as that boot seal is moved. And as I mentioned, there's contact everywhere. And there's also multiphysics here. With this kind of coupling, you actually include all the different nonlinear effects into one and the same model. And so these researchers, I should give credit here, it's Luca Armelin and Fabio Gattelli. They were able to create a model that was that reduced the number of prototypes that you make, and you can save hundreds of thousands of euros if you can just reduce the number of prototypes from 100 to 10 or from 1,000 to 100. There's a lot of benefit in terms of them being able to do this. And so as they developed the model, they were able to include more and more realistic materials to the model and get better and better results. So this is the experience of Metelli. I believe this type of simulation where you kind of refine your model step by step to get more and more insight into the design and to the physical performance of the model is something that that is the real benefit of simulation. Okay, so with that, I'll just mention on my kind of wrap-up slide here, multiphysics and mechanics. One thing I didn't cover that we that we actually handle in COMSOL is something called creep, and this is an effect where under constant load, materials start to behave differently, and most of the time this is categorized under thermal creep. Although there are other ways of having creep without any kind of multiphysics, but so I kind of categorize it as multiphysics as kind of an easy way out. But basically, what you do here is you actually solve another equation. Basically, the strains become time dependent. There's a strain rate that you need to consider, which is a function of the various load. Could be a function of temperature, for instance. And so that creep will affect the way that the stresses and the strains are related in your model. So that's something that you can also do using the COMSOL interface. We also have a lot of what we call predefined couplings in COMSOL. In other words, these are things that kind of come out automatically with COMSOL. We've put them together for you beforehand. So for instance, for piezoelectric effects. For those of you not familiar with the term, this is basically materials whose electric behavior changes with relationship with the stresses and the strains. So when you displace a little piece, it'll either have it'll conduct electricity or the opposite. And the same way the other way around, where if you put a current through a piece of material, there'll be stresses and strains. Acoustic structure interaction, obviously when you have loudspeakers and this type of behavior, you have this kind of relationship between the fluid domain and the solid domain, and that's what acoustic structure interaction is all about. A lot of care has to be taken at the boundaries where you want the pressure gradient to be proportional to the strain on those boundaries. So that kind of thing is, we've kind of taken care of that for you with the acoustic structure interaction. Thermoelectric structure interaction, I think thermal actuators are kind of the obvious thing here. When you pass a current through a conductor, there'll be a little bit of structural change, and this is especially important for the MEMS field. Fluid structure interaction is a very common thing here. You can actually see an example of that in this well-bore model. This is a kind of a multilateral well. If the picture on the upper right, that model uses poroelastic effects together with porous media flow to give you the different stresses and strains on the soil and on the walls of the well. It's very important for oil and gas industry. And then thermal structure interaction as well. COMSOL also gives you the availability to do general coupling. So if you want to couple something together that might be kind of exotic, you certainly able to do that. Maybe there's some kind of chemical reaction happening on the boundary, etc. So those are the kind of things that you can do with COMSOL as well when you're doing your nonlinear analysis. Okay, and so that's it from my side, and I guess at this point I'll pass it over to Laura.
Okay, David, thank you very much. Great presentation. Now the remaining time will be open for questions, and there are a couple of them posted, and I'll just read the first one. What is the minimum system requirements to operate COMSOL?
Okay, so I guess that one's for me. Let's see, that is a good question. We actually have a system requirement web page that kind of gives you the latest and the greatest. At this point, I believe we highly recommend, maybe not yet require, but highly recommend a 64-bit system. And on that 64-bit system, at least 1 or 2 gigabytes of RAM. You know, as time goes on, memory becomes cheaper, and so hopefully that is within the realm of most. We do actually still run on 32-bit, but you know, doing 3D models on a 32-bit computer these days is probably a test of patience. And so if you're a very patient person, then you can do that.
Okay, very good. And here's one for either one of you. The attendee says, I've been trying to generate C waves and its effect upon buoy to measure output of the buoy. I'm getting stuck during the process. Can you help me regarding this?
Could you please repeat that again, Laura?
Okay, sure. I've been trying to generate C waves and its effects upon buoy to measure output of the buoy. I am getting stuck during the process. Can you help me regarding this?
Yeah, at this point, I'm not sure what solution he's using, but if MSC has a fluids CFD code, so this probably falls more under CFD rather than structural mechanics, unless he is studying the buoy itself. But yeah, if he can contact me, and we can get more details and figure out yeah, which one, whether it would be a CFD problem or a structural one, and we can figure that out.
All right, very good.
Yeah, I just kind of, you know, endorse that statement. You know, a lot of times people have an idea of what they model, that they want to model, but the devil's in the details. So you want to kind of get really into it before you can, before you start doing those simulations. So kind of having a kind of finer scale understanding of the problem before doing simulations is usually the best route to take.
Okay, good advice. Here's one for both of you. What type of material properties do we need to model nonlinear analysis, and how do we get these properties?
Yeah, I can take that. So these, it depends on the type of material that you're trying to model. For example, standard metals, let's say steel or aluminum type of metals, the data is generally available. There are some databases that you can get the data from. But let's say you are looking for some kind of specific rubbers. When you're looking at elastomers, there are, as David mentioned, it's not like your Young's modulus and Poisson's ratio thing. You need to get some kind of energy function, which means you need to conduct the stress strain test under certain conditions. So it generally, again, there are classes out there, and we also provide some training and some documentation as well. I'm sure COMSOL also does a similar thing. So that you need to understand what is there. So most of the times, if you just contact the manufacturer where you're getting the material from, you may not get all the actual information that you need for the analysis. So that is one thing you need to be very careful about.
Yeah, that's right. Sometimes these things are patented or trade secrets, so they actually won't tell you exactly the material. Especially if it's some kind of groundbreaking material that makes a lot of money for a company. You're not going to get their secrets out necessarily. But there are a lot of textbook examples that you could start with.
Okay, very good. Thank you. Here's one for you, David. Specifically, can you please explain fluid structure interaction, which is in model tree?
Yeah, so there is a, just for the general audience, there's within COMSOL we have these kind of we have this approach of doing a tree structure of doing the simulation, and basically, just briefly, what that is, it's a automatic coupling of a fluid model, a CFD model, together with a solid model, a mechanical model. And so, we'll take, the general, whatever CFD model, just take, for example, a Navier-Stokes type of equation and couple it together with a, a general solid model. And the way that we kind of transfer the two would kind of depend on how you'd like to link those. And typically it's through a boundary condition where the acceleration on the boundary is proportional to the velocities that occur next to the structure. And so that's kind of how it would work. And you'd need to set it up. You'd have to get the stress constraints down. The loads, like I said, would be automatically set up. You have to set material properties and those type of things. But yeah. So that's in general what, referring to this tree structure, that's kind of how it works. You get basically all the specifics of the physics model together in a batch like that.
Okay, thank you. Service, this attendee says, if I've been doing linear analysis, how much additional effort does it take to learn and perform nonlinear analysis?
Okay. Yeah, that's a good question. One good thing is, looks like you have a good starting point with the linear analysis. So you do understand some of the issues with conducting a finite element analysis. But when you go with nonlinear, of course, there are issues like the mesh size, and as both of us were talking about, where the stresses could be higher and what kind of nonlinearities. So you would need to understand some of those things to get better results. Again, you can get any result, but the main thing is to get accurate results. You need to have a good idea about, again, what type of materials and also what kind of nonlinearities. So learning that, I would say you need a little bit of background. And again, there are training classes available by, again, all of the vendors where you can get the some basics of required for the nonlinear analysis. And I would say, like, for example, at MSc we offer either a 3-day course or a 5-day course, depending on your need, or even training notes that you can access. So so using those examples, you should be able to come up to speed quickly, depending on what other codes you have been exposed to.
Okay, thank you. This attendee asks, and David, you may have hit on this in your presentation, is it possible to simulate clay, in parentheses, soil, for design die extruder?
Let's see. I know what clay is. I know what soil is, but I'm not sure what a design die. Oh, okay. I think I understand. Okay, yeah. So, wow, that would be interesting. I think there might be one or two things you'd want to do there. So the extrusion process, typically you kind of consider the thing that's being extruded as a flow, as some kind of non-Newtonian fluid as it goes in there. But you're just pumping in clay, though, huh? That's interesting. I think that kind of thing could be modeled in COMS. Of course, we'd have to discuss the particulars of that. We do have people doing extrusion processes, though, like with sheet metal, etc. And so the important parts there, I guess, would be the contact and the getting the material properties right. Yeah, so maybe, if that's a good answer. A definite maybe.
Okay, thank you. Now, this question doesn't refer to either software, so maybe both of you might want to take a stab at answering it. It says, you mentioned that the program automatically refines the mesh in areas with high stress gradients. How important is it to have refinement in regards to the load step spacing?
Yeah, it is. So depending on the stress, because for the gradient, so whenever what happens is in the stress concentration region, like for example, a notch area, you definitely need finer mesh so that you capture that gradient. So that is where, as long there are certain criteria based on stresses or strains and contact and several other conditions, and of course user-defined conditions. So to get that better result accuracy, like to capture the local high stresses. Otherwise, there could be high stresses which might lead to failure, and you may not be, if the mesh is coarser there, you may not be able to capture it very well. So that's the reason it is very important to capture those areas.
Yeah, I think the meshing thing is always a big point in terms of when you're doing FEA, mechanical analysis, and it's one of those things where it's garbage in, garbage out. So if you have a very coarse mesh, yeah, you might get a solution, but it might miss the area where all the action's taking place. And so that's kind of the idea behind refining in the areas of where the gradients. In other words, gradient refers to change, and so where there's a lot of changes, that's where you really want to focus in on what's happening. And so that's even true for like when you're looking at a TV or something like that. You want to have a high definition, especially in the areas, if it's a white screen, it doesn't matter what the definition is, but when there's a lot of action taking place, like a football game or something, you want to have very high definition, especially where there's a lot of action taking place. So yeah, and of course, meshing isn't free. You always have to pay for it with computational considerations as well.
Okay, we have just a few minutes left, so I'm going to take one last question here, and it doesn't here again refer to either one, but both of you want to answer it. Will the program automatically add load steps if the solutions between two adjacent load steps are drastically different, or is this not important?
I can just make a quick mention and pass it over to Srinivas. But the way that COMSOL works is we do have what we call a parametric solver. So I believe what you're talking about in load steps is you're talking about you have a structure under load, and you want to kind of keep increasing that to kind of see where things start to break down, or maybe to see the performance under different scenarios. And so COMSOL will actually try to take the parameter steps that you give it. So it could, and this is true for anything, including non-mechanical models. But anyway, for mechanical models with the load, you'd put it at whatever those load steps might be. And then if COMSOL doesn't converge, okay, of course, converge is a technical term in computing, but basically whether or not you get an answer that's close to being right. If you can't converge, then COMSOL will automatically put in intermediate load steps there to get you to the right answer. So that's kind of how COMSOL works with the parametric solver.
Yeah, that's true. But that's one thing in nonlinear solvers. Whenever you apply certain load steps, loads, it is an incremental approach. Actually, it's an incremental and iterative approach. That's what it's called. So it has to be broken into steps, and when something doesn't converge, yes, it has to be, it has to take smaller steps, and those things, yeah, they're done automatically. If you want to control, yeah, you have the control, but most codes, again, we also provide flexibility so that you have, you decide how you want. Because the reason the user has control is sometimes you want results at specific data points, and if you let the program take care of it fully, yeah, you may lose some control. So sometimes you may need a combination of both. So that is why you can go either way. You can have full control, you can have the program to fully control, or a combination of those.
Very good. Well, Srinivas and David, thank you so much. You put together some great presentations, and thanks everyone for attending this webinar from Design World. This presentation will be emailed to everyone later today and will also be available at designworldonline.com. Thank you.
Thanks.
Thank you.